So, so we'll have two classes, one today and one on Wednesday, Tuesday. So today's class, so we are sort of talking about the interstellar medium in this last third of the course. So interstellar medium is all this gas, uh, dust, magnetic fields, cosmic rays, turbulence. Very very complicated system where we still don't know a lot of things about. So, uh, so we had covered uh, like 21 centimeter basic radiative transfer. We covered, it's a modeling of absorption lines. We talked about ISM and so on. So uh, now we'll be talking about dust. So dust, what is dust? So there's gas. Gas occupies all the available volume, right? So dust dust particles are solid particles, right? They don't occupy the whole available space. They don't have pressure. They don't exert pressure on the walls of the container, unlike dust. So dust is like tiny solid particles. Okay. Uh, so being tiny solid particles, they are also dense, right? So the average density of dust particles is like average density of a solid, like few grams per centimeter cube. Right? Whereas the gas density, the gas number density is 0.1 particles per centimeter cube. If you spread the gas out uniformly, that's the density that you get, which is like 10 to the minus uh, 27 or minus 24 grams per centimeter cube. Whereas this is 1 grams per centimeter cube. So dust is really like a solid, small but solid thing, uh, distinct from gas. Okay. So these are micron size particles. So this is interstellar dust. And the interstellar dust is very much like our terrestrial dust in the sense of small size, sediments in gravity, uh, does not occupy all the space, right? So just like dust, when you sort of uh, broom in your old hostel room, the thing that blows is the dust. So it's very similar to that, micron size. And we still don't understand how it forms, uh, where does it come from, and so on. We do have some hints, but not very solid details. So these are micron size particles, and they constitute about 0.01 or about 1% of the mass of the interstellar medium. So by mass, they are not, dust is not a major constituent of the interstellar medium. Yet they are very, very important because it affects the radiative properties of galaxies, right? We even at the very beginning, we were talking about how the presence of dust makes the galaxy appear red, right? So it's very, very important for, even though it's subdominant by mass, it is very important uh, because of observational consequences. The other thing is dust plays an important role in almost all aspects of interstellar medium. We talked about uh, cooling and heating of H2 regions, for example, in the last class. So if dust is present, dust can block some of the ionizing photons, and uh, dust ionizing photons or even lower energy photons can actually eject photoelectrons from dust and hence heat the gas. So dust plays an important role in thermodynamics of interstellar medium. Uh, Dust, so H2, molecular hydrogen that we have in the interstellar medium, is supposed to be catalyzed by dust. Molecular hydrogen is supposed to form when a hydrogen atom sort of is captured on a dust particle, uh, and it stays there, sort of moves around on the dust particle, and another hydrogen atom comes, and when they recombine on the dust. So dust is a place where a lot of chemistry happens. Dust is also very important. Uh, People talk about planetesimals. In planet formation around stars, you want to grow planets, and planets are sort of solid objects. So the story goes that you form small dust grains, and they sort of collide and somehow become bigger and bigger to a size beyond which self-gravity can take over and sort of can grow the planet further. So you can actually see that dust processes are extremely important for a lot of aspects of ISM and beyond. Okay. Um, so, so it causes extinction and reddening. So what is extinction? Extinction is dimming, basically. So if you have a if you have a background source of light and there is dust in the intervening medium, uh, dust can absorb radiation, dust can scatter radiation out of the beam. So absorption plus scattering is extinction, right? So there is a difference between absorption and scattering. In absorption, the photon is lost. In scattering, photon is sort of thrown out in another direction. Okay, but from the beam that from beam of photons that are coming towards you, both of them remove photons. So both of them cause extinction. Uh, dust can polarize stellar lights. So the stars are black bodies, roughly, and their radiation is unpolarized. But if you have dust in the intervening medium, it can polarize the light of the background stars because it can. So for two reasons. One, dust particles are also not spherical; they can have complicated shapes, and because of that, uh, if they are, so say, let's say they are spheroids or uh, uh, ellipsoids, and if they are aligned, say due to magnetic field, so dust grains can also be charged, right? Because they're exposed to all this plasma, and they can get charged because of that. So eh, they can have magnetic moments, so they can actually get aligned with magnetic fields in the interstellar medium. And because of that, so if the dust grains are globally aligned, and if you have a background source of light like star, uh, it can preferentially absorb one of the polarizations of light because you have absorption which is differing in one direction compared to other. So it can produce few percent polarization of stellar light. Um, So you can have emission due to dust, right? When I sort of showed you this broadband uh, distribution of light in the universe, there was CMB and so on. But there, in infrared, there was like a big black body-like part which was due to dust heated by stars and re-radiating in infrared. Uh, it can also emit in microwave. It causes a lot of problem to people who study the CMB because it sort of emits in the same region. So you have to actually take this out carefully in order to get to the cosmic microwave background. Uh, dust can also luminescence. It can also shine due to luminescence. So luminescence is like uh, phosphorescence. You absorb a high energy photon, uh, and the molecule or whatever, the dust, excites to a metastable state and then produces a low energy photon after that. So there are some minerals which also show this property. Uh, right, so it does the same thing. So the point is it has a lot of complicated processes associated with it, and they are also important. Um, okay, and in principle, you can produce a lot of absorption by less amount of mass, right? All you need to do is provide a screen which covers or blocks your line of sight. So even small amount of mass can block a lot of light. But how do we know that mass of the dust is about 1% of the ISM and not 10 to the minus 6 or smaller? And there is a very useful and very physics-based limit given by Purcell. Uh, which sort of, it's sort of based on basic properties of dielectric. So the absorption properties and the propagation properties of a dielectric are related through something called Kramer's-Kronig relation. I don't know if you have done it, but there is a relation between absorption and propagation of background light for dielectric materials. And if we assume linear dielectrics, then using those arguments, Purcell produced this limit that the dust mass has to be about 1% of the ISM mass or the hydrogen mass in the ISM. We are not going to go through the argument here, but it's important to know like that there is something like this that exists. Okay. Otherwise, you could have said, okay, dust mass is tiny. Okay. The other thing is, if you look at the gas phase abundance of certain elements, like oxygen, aluminum, silicon, carbon, you find it to be less compared to the abundance in solar photosphere. So the interpretation of that is a lot of these abundant elements condense into dust. and are sort of reduced in the gas phase, which you are sort of observing in your absorption lines, for example. So I already mentioned molecular hydrogen is catalyzed by dust, and photoelectrons produced by dust can produce heating in the ISM. So these are some of the important things. We'll slowly go through each of these things one by one. Since there's only one class, I didn't really have a lot of there was no time to work things out. So I'm just going to tell things and mention uh, ideas on the way, but not quite derive things. Okay. So the first property of dust is this extinction, right? Uh, so you remember, like in this whole debate of um, island universes, the thing that we started this course with, right? There were these two parties that said that other the nebulae are other galaxies like our own, versus that they are things within our galaxy, they are clouds within our galaxy. That puzzle, one of the uh, key hints to solve that puzzle was through dust, right? That uh, this Captain universe is tiny because a lot of these stars are just absorbed by dust, and you sort of find yourself in the center of a small uh, galaxy, right? So by sort of measuring, mm, so by measuring star clusters, right, this Trumpler uh, found that the farther, the smaller the star cluster is, it appears more dimmer than what its distance would suggest. So if you assume that all star clusters have roughly the same size, what he found was that the star clusters which are small in angle, small angular size, you roughly know their distance, or you know the relative distance relative to something which is a bigger angular size. But if you look at the flux, it's much smaller for the farther uh, star clusters, and that's because of additional absorption by dust. So that's how people came to appreciate that almost all sight lines have absorption uh, due to dust. Okay, so this is the plot of something called A lambda. So what is A lambda? So this is the definition of A lambda. This is called extinction. A lambda is extinction at wavelength lambda, and its units are magnitudes. So it's just 2.5 log 10 unobstructed flux divided by the observed flux, right? If F lambda naught is the flux of the emitter, and if F lambda is the flux that you observe after absorption, this is uh, this is the definition of A. And since F lambda is e to the minus tau F naught lambda, A lambda is just given by this, right? That it's just 2.5 log e to the optical depth at that wavelength. And if you just do this math, you get this. So A lambda, or extinction, is roughly equal to the optical depth. And the need for this type of unit is because you're dealing with magnitudes, and this 2.5 log uh, appears when you're dealing with magnitude. So if you want to know the magnitude of an absorbed star, what you do is you just add A lambda to it, so that you get the apparent magnitude after dust absorption. Okay, but the point is it's proportional to tau lambda, which itself is proportional to the column density of dust, or whatever the absorber is. And if the dust is well mixed in the interstellar medium, that is, roughly the same mass fraction of dust everywhere in the ISM, then A lambda would be proportional to the column density of hydrogen, right? Because if the mass fraction is the same, if you have certain amount of column density in neutral hydrogen, you'll have about a proportional column density in dust. So that's why you normalize your extinction with the column density of hydrogen. So this is about so this is how it looks like. So A lambda is in magnitudes, and column density is number per unit centimeter squared. So what do you mean? How do you interpret it? So a value of 1 here means 1 magnitude extinction for every 10 to the 22 column of hydrogen. Right? So 1 magnitude of extinction means that your flux is decreasing by uh, so 2.5 magnitudes means a factor of 10 decrease in flux, right? So 1 magnitude is 1 by 2.5, which is 0.4. So your flux, so for a column density of 10 to 22 in neutral hydrogen, uh, your flux decreases by 0.4. That sort of is the interpretation, roughly. In like, unless you're looking through a very dusty region, this is like the general value. Uh, or not a very so unless some region has very peculiar dust, right? Because it's normalizing with the matter amount anyway. Okay, so this is how it looks like. This x-axis here is lambda inverse. So we know that there is more dust absorbs more in UV, much more in UV compared to infrared. So this is lambda inverse is 10 micrometer inverse. So this is like 0.1 micron, 1,000 angstrom, right? We don't go beyond this. We don't go to the right of this because 13.6 eV is like something which, if your photons having energy higher than 13.6 eV or lambda smaller than 912 angstrom, everything will be absorbed by neutral hydrogen, right? Because hydrogen is sitting in ground state and you form an H2 region as soon as you have photons available at those energies. So here you only go till about 0.1 micron. Uh, so you have maximum absorption here and you have minimum absorption here. So this is about 1 micron infrared. This is like 0.5 micron. So this is sort of visible UV visible. Uh, the inset shows the extinction at lambda greater than 2 microns, so which is this part. Uh, so this is lambda inverse. So yeah, lambda greater. So this is 0.5. So lambda greater than 0.5 is shown here. So this is absorption in the infrared part. In fact, in this absorption thing, you actually see these features. And these features actually are like bands or sort of so they are like dust grains are more complicated than atoms, right? They don't have very simple lines. They have like complicated bands because there are so many degrees of freedom. They can oscillate and vibrate and do things in more complicated ways. So in fact, you do see these sort of features in your absorption, but people don't quite understand a lot of these features. A lot of these features, especially here, are not identified that this is this mineral, this composition of dust gives rise to such emission and absorption features. Here, in infrared, they sort of think that this is a silicate feature at 10 micron. This is some CH bond, uh, which sort of gives this feature at 3.4 microns. So there's a lot of like synergy with chemistry as well. People who do spectroscopy and chemistry in the lab give a lot of input to people who do these kind of observations. This is also another common feature, this 2175 angstrom ultraviolet feature. You see this, and you can see this question mark. Is this aromatic carbon? They don't know. I mean, this is a guess. So you see, even such important feature is not quite identified very certainly. So this is the silicate feature that is zoomed in here. Right. So dust not only absorbs background radiation, it absorbs much more at shorter wavelength. So be careful. This is lambda inverse. So shorter wavelength is on the right on this. Not only does it absorb, dust also reddens background stars, right? Because it's absorbing more in blue and UV compared to infrared. So a star appears redder if it is obscured by dust. And the more the column of dust, the more red it will be, right? So reddening is this quantity, AB minus AV. Reddening is this AB minus AV. So what is AA is this, A is defined as this value, but A is proportional to the optical depth. It's about equal to optical depth, you can actually see from here. So B is B band, V is visible band. So it's sort of like blue minus visible. So it absorbs much more in blue compared to visible, right? So AB, the value of tau in B will be larger than value of tau in V. So, so this is basically differential extinction, and this is total extinction in V band. So reddening is so this parameter RV is a parameter. So you can actually have somewhat different extinctions along different directions, right? And that sort of reflects some compositional variations of dust. So, for example, this is This was just one of the. So yeah, let's see. So this RV is this parameter, which is the ratio of visible extinction to reddening, right? If all the dust was universal, RV should have been a constant, because the more the column you have, the more you absorb in V band, and more. I mean, and the same is the difference between B and V band absorption. But that's not the case. Uh, you see somewhat different values of RV, a range of RVs in real interstellar medium. So instead of this plot for A lambda versus lambda inverse, you get something like this. So in infrared, more or less, uh, RV does not matter. A lambda is more or less the same. But in UV and optical, they sort of depend on this RV parameter. So this is just a common parameterization that's used. So if, for example, if you observe a high redshift galaxy, what do you use to model it? So you choose one of these curves and you say, okay, it has an RV of this, this, this. Let's see if it fits the broadband observations that we have. Okay. These features here at about 0.5 micron are called diffuse interstellar bands, or DIBs. As I said, a lot of these are not even identified. What what uh, uh, what mineral or what composition does it correspond to? Okay. So you see, for example, here RV value is 5.5, 4, 3.1, and blah blah. So if RV is uh, large, you have less absorption in UV. So yeah, you can actually see this difference becomes large. If this difference becomes large, then RV becomes, if this difference is small, the RV becomes large, which is what it is, right? In the UV side versus optical side, the difference is not that much as compared to here. So this is why you can mark with these. In fact, I was reading Drain's book, and there are like 7 parameters that you can use to like quantify dust absorption and dust extinction and reddening. But this is reasonably decent. For example, this particular thing, this dash line is no, this dot dash line, this one, HD 210121. This is extinction along the line of sight to this star. It does not quite match this 2.1 value, 2.1 model, but it roughly is okay. So these, everything else apart from that HD 210121 is a model. Okay. Okay, dust polarizes starlight. So here is a map of, so this is polarization of 2,765 stars within 1 kiloparsec. So within 1 kiloparsec of our sun, you look at all the stars and look and mark their position. So this is L versus B. L is galactic longitude, B is galactic latitude, right? So you look at, so this is the galactic center, this is L, and this is B, right? So these are all these 2,765 stars, and the dot shows the position of the star, and this line shows the polarization strength and polarization angle. So you see, so a lot of these stars which are in the galactic plane have high polarization and have their polarization angles in the plane of the Milky Way. The guys which are at the high, high B's, so they're like, they don't have as much column in the interstellar medium. They have low uh, polarization. So polarization is caused by dust. I mentioned previously. So because of non-spherical asymmetric dust, which is aligned along local magnetic fields, you can get more absorption of one component compared to the other. So this is why you get this polarization. In fact, this is how the degree of polarization is observed to go like with lambda. So, oops. So polarization as a function of wavelength. So this is just an observational fit uh, to this kind of data. That if you do the same exercise at different lambdas, you find that the polarization peaks at a certain lambda max, and it has this kind of a distribution that at both high lambdas and at small lambdas, polarization decreases. Okay, and the value of this lambda max is around 5,500 angstrom. So this actually tells a lot about dust. So what it tells is, right, so as we move further, we'll see that dust absorption. So if you look at absorption due to dust or extinction due to dust as a function of wavelength at in the low wavelength limit, right? So the low wavelength limit is just the geometric limit. It's just the area of the dust particle which blocks the light. As you go to long wavelength limit, you are in the Rayleigh limit of scattering. In that case, absorption becomes smaller and smaller. So the fact that you have this sweet spot in causing polarization means that you have to have, at around this wavelength is where you have maximum absorption for particles are of those size. So it sort of picks out the dust particle size, right? So 0.5 micron, it picks out. So that's why these kind of observations are very useful. Yes. Yes. So for example, all these directions of polarization tell us about the magnetic field direction. So in fact, this is used quite commonly for people, people studying the ISM. Archana Som at IA sort of works on this kind of stuff. Okay. Right. So the other thing is uh, the P max is, so the more the column, the more polarization you will have, right? Because the differential absorption will just be integrated along the line of sight. So P max is roughly goes like this. So it does, but this is an observational thing. I mean, this is not a model. This is how you see polarization. So your dust has to have these kind of properties, is all I'm saying. So, so this is how P max goes with AV. Higher the AV, higher is your P that you expect, the polarization fraction. And similarly, AV itself is is proportional to reddening. So they are all linearly proportional to each other. So this is a cartoon diagram of what may be happening. So if you have magnetic field like this, and this is a dust grain, and it aligns like this. Okay, so this thing about the dynamics of dust and how it interacts with magnetic field is non-trivial, extremely non-trivial uh, exercise. So it can precess, it can sort of align slowly or misalign. So there are torques, radiative torques happening. There's a lot of physics going on in there. But this is what is thought to be that dust can align like this with its minor axis along the direction of magnetic fields. And if magnetic fields are coherent over some length scale in the ISM, this polarization and so assume that our line of sight is into the plane, right? So this polarization of light, of the background light, and this polarization of background light will suffer different absorption. Right? It's sort of like when you do optics and you have these optical elements, like if you sort of create like a thin wireframe material like this, and if you sort of rotate it, and if you have an unpolarized light in the back, you can polarize it along this direction. Right? So that essentially does the same thing. The other thing is it may be that only certain size dust is able to quickly align in this way. So this observation of polarization tells us a lot of things about the dust dynamics and magnetic fields. Okay. Dust can scatter. So we have to be very careful with the terms that we're using. Extinction is basically anything that takes away light from the beam that's coming towards you. So both scattering and absorption adds to extinction. If you look at scattered light, so for example, if you don't have these lights here, and if you just go out and don't look directly towards the sun, the light that reaches your eyes is the scattered light, right? So it's the light which is coming from these oscillating molecules in the air, in the atmosphere. So, so if you look at diffuse regions in the ISM, uh, a lot of times you can actually catch scattered light scattered due to dust. Okay, so for example, if you look at the diffuse galactic light in this lambda wavelength, again this is lambda inverse on the x. Uh, these are observations, and here this Murthy is IIA Murthy, because he's sort of he's worked a lot on UV uh, UV instruments. Jayamurthy. Right. So these are observations of albedo. So what is albedo? Albedo is fraction of scattered light divided by total attenuated light. So attenuated includes both absorption and scattering. So so albedo is less than 1. Okay. Uh, so this is how albedo goes as a function of lambda inverse. And these are the data points. The solid lines are some dust models. You can actually see these RV labels. You see, not all the data goes through the models. So, this is an extremely complicated field. But this data does tell you about what the properties of the dust should be. Okay, so this is through the some diffuse region. This is in some cloud. This is in some reflection nebulae. So nebulae, these like H2 regions, also have dust around them, and you can see light so you can see dust scattered light from these nebulae. In fact, you can actually, if you don't look directly at the star, but if you look at the nebula, you can even see the absorption lines of the star in the reflected nebula, because the same photons just sort of get uh, essentially reflected in other direction. Okay. So this tells us about scattering properties. This here is mean of cos theta. So the following is the scattering problem. So you have a scatterer, you emit a beam of radiation, and the beam gets, particles or the photons in the beam get scattered in different directions. Okay, some in the forward direction, some in the backward direction. And if you assume the the scattering to be uh, axisymmetric, so that it only depends on theta. So the angle is your line of sight to the dust grain, and this angle theta. Okay, and this is phi. The phi direction is sort of symmetric, so you can assume phi direction is symmetric, but theta direction is not. Uh, so if you have, say, Thomson scattering, Rayleigh scattering, all of them are symmetric. Scattering in these regimes are symmetric with respect to uh, this 90 degrees. So the probability of being scattered slightly, at the same angle away from the perpendicular and towards you in the perpendicular is the same. So whereas for dust, the scattering is mostly forward scattering. So if you have dust and if you have background light, most of the light will be scattered in the forward direction. So this mean cos theta, if it was Rayleigh scattering or Thomson scattering, mean cos theta should have been 0, right? Because theta is this angle between the line of sight and this perpendicular. But you can see I don't really know how they're able to measure this, but if these are the observations, what it says is that the dust scattering is very forward, very much biased in the forward direction in all these places. So it is not simple Rayleigh scattering. Okay. So this is about scattering. So absorption, scattering, emission. So we know that dust can be heated by starlight and it can emit as black body. So if you look at this nu I nu by nh, so you'll always see this nh scaling because more the column, more the emission for optically thin emitters, and and also this goes as absorption. So this is the observations in, now this is lambda, not lambda inverse. So this goes from 3 microns. So this is all near infrared to far infrared, 3 micron to 1000 microns, and sort of although it shows lambda, it is sort of like lambda inverse because the axis is reversed, right? So lambda increases towards the left. What do we see? So this these squares, these are from observations. This is Kobe Firas. So this is a CMB experiment, right? Kobe was the CMB experiment that measured emission due to dust, and it sort of looks very close to a black body. This is just heated dust at around 100 Kelvin. CMB would be here. CMB peak would be here, but that's not shown. So this is black body, and this is not. These are also observations, and then at around so these are some of the emission line features from dust particles. These are called PAH emission features, polyaromatic hydrocarbons. So they are like benzene, but like large cyclic rings put together. They're very complicated molecules, and some of these features are thought to be from there. And if you look at amount of power emitted across these wavebands, you see at wavelengths greater than 50 micron, you have about 65% of the dust emission comes in far infrared. So this is emission. This is the heated dust emits this. So scattering, emission, attenuation, all these are related but different quantities. Yes. Yes. It's assumed that the dust is well mixed in the ISM, in the diffuse ISM. Yes. And that sort of seems to go together. So if you look at more high column density regions, you also see higher A lambda. Yes, that is also correct. The higher the density is, the high density regions are places, high density cold regions like molecular clouds and so on are places where dust must form. But the understanding of how dust forms is still not very good. I mean, there are so in fact we do know something. So AGB stars, though, so after the main sequence, the sun-like star or slightly more massive stars goes through this AGB event phase. They evolve off the main sequence and they produce dense cold stellar outflows in which a lot of dust can condense and it can just go into the ISM. You can also form dust in supernovae. So you can form these self-shielded regions in supernovae, where dust can condense and can be thrown out. So if you look at even in 1987A, this supernova that happened in 1987, people actually saw spectral evidence for the formation of dust in the ejecta of the supernova. So these are some places where you observe dust to be formed, but how it forms, the physical process is not very well understood. And once formed, it should also be sustained. It should not just be evaporated immediately in the interstellar medium. So it has to be in regions which are cooler, because if you expose dust to very high temperatures, it just gets evaporated. Okay. Now, this problem of how dust grains scatter radiation is a classic problem of scattering of light by particles. Okay. So the setup is exactly so. You have a grain or a lot of sort of particles together, and you have, say, a linearly polarized light emitted on it. Uh, you can actually think of these particles on the grain as like little dipoles. They can also start oscillating because of getting excited by this electric field. These oscillating dipole will radiate energy in all directions, and all these dipoles will add and produce radiation in different directions. So the light ray which was moving in this direction, now some of its power is going in other directions. That sort of is the picture of scattering. Okay. So here are some of the notations, at least. So since we don't have an, I mean, this is a classic problem in E&M, right? To solve for the E and B in the in the radiation limit, in the far field limit, given this emission incident radiation. So your material response will produce that. So we cannot do that in this class, but that is sort of the idea. So, but these are sort of the notations. Okay. So this CABS is absorption cross section. and it's a function of lambda. We talked about this Rayleigh limit, right? We know that cross section in the Rayleigh limit goes like lambda to the -4, like this, the classic thing, why the sky is blue and all that. So that's we know that the cross section for scattering goes like lambda to the -4, not absorption. So dust grains do both absorption and scattering, and all these properties are functions of lambda. So these are cross sections: absorption cross section, scattering cross section, and extinction cross section is just the sum of the two, because both absorption and scattering extinct the light from a background source. This is the albedo omega ratio of scattering cross section to absorption plus scattering cross section, which is this. Uh, differential cross section. So these kind of ideas apply to all sort of scattering, like even quantum scattering, LHC, how many particles go in which detector and so on. So differential cross section means how what's the probability of scattering at an angle theta. This one. The mean value of cos theta, we already saw the figure for this. This is the definition of mean cos theta. So this is the differential cross section area per unit solid angle, d solid angle times cos theta, and integrate over all angles. So this is your definition of cos theta. And I already mentioned Rayleigh scattering, Thomson scattering, which is sort of dipole scattering, gives you this 0, right? Because this dc d omega is symmetric about theta equals pi by 2. From that symmetry, you get this to be 0. And sometimes these cross sections are normalized to the geometrical area of the dust grain. So this is the scattering cross section, which is also an area. Cross sections are areas. And this is the geometric cross section for scattering and for absorption. And there are various ways in which you can define this effective radius of the grain. This is one definition in which you say that the volume, so if it is a complicated shape, you just say that the volume, it has the same volume as a sphere of size A effective. So 4 pi by 3 A effective cube equals V. This is the definition. Actually, dust also plays a very important role in dynamics, because the dust absorption and attenuation cross sections are pretty high. So if you have a dusty region, and if you have a bright source of light like AGN or like stars, massive stars, then the photons, the optical and UV photons from that source can actually kick the dust particles, and because the photons carry momentum, and the dust can get that momentum once the photon is absorbed or the photon is scattered. So this is the expression for radiation pressure cross section, CPR. This is absorption cross section. Of course, if the photon is absorbed, all that momentum that the photon had now goes to that dust particle. And this is 1 minus cos theta c scatter. In scattering, what happens is you have a photon coming in this direction and it goes in that direction. So that's why you have this 1 minus mean cos theta. So if you have a photon which goes in this direction, it does not give the dust as much momentum compared to one which goes in the backward direction. So that's why you have this dependence. And once the dust gets momentum, it collides with the gas around it, and eventually the momentum is transferred to bulk of the mass in the ISM. And then you can also use degree of polarization for light scattered through an angle theta. I mean, these are just the notations. Okay. So setting up the scattering absorption problem. So these are the equations, of course, right? So these are, Maxwell's equations in presence of sources. And so basically the setup is you have a, say linearly polarized light, which sort of, you can take it as a plane wave. So e to the minus I omega t plus I k dot x. This is how it varies in time and in space. And in general, for a dust particle or any dielectric material, you quantify its response. So, if you have electric field to which a material is exposed, it can get polarized, right? The charges can move around and shield the externally applied field and so on. So that's sort of, that's the definition of a dielectric. And the response of this material is quantified through this dielectric function epsilon, which is a function of frequency, right? So it has a real part and an imaginary part. The real part is what we mostly sort of deal with normally through things like glass and stuff, which do not absorb. But if you have metals, they have a imaginary part of the dielectric, which sort of causes this attenuation of radiation inside metals. Okay, we do not need to bother about mu because the magnetic response time is too long uh, for these frequencies because the magnetic properties of these materials come from their spin or orbital angular momentum, and their sort of response time is much longer than these gigahertz frequencies that we're talking about. Um, so we just need to like worry about the electrostatic response. Uh, this m is the refractive index, right? And m is just square root of epsilon. So since epsilon is a complex number, this also is a complex number. Refractive index in general is a complex number. And this is the relation between, so you have imposed a frequency of the incident radiation. Now K is what is chosen depending on the material property. So K is just square root of epsilon, which is nothing but the refractive index times omega by C, right? So omega equals CK in vacuum. So M is 1, refractive index is 1, or epsilon is 1. Uh, Otherwise, uh, in a normal material, if you have a non-zero epsilon 2 or a non-zero imaginary part of your refractive index, your electric field can get attenuated inside that medium. So something like this. So electric field is proportional to minus imaginary part of m omega x by c, right? So if you just substitute k equals this there and assume propagation along x, this is what you'll get uh, for the damping part of electric field. Now, we won't really go through working all this out. It's actually quite complicated. Uh, But what we'll do is we'll just mention the results, okay? This limit, when the grain size, the particle size is much less than the wavelength, right? Rayleigh scattering, the reason why the sky is blue is also Rayleigh scattering. The molecules in the atmosphere are of order few angstrom. The wavelength that we're seeing is 0.5 micron. So A of the molecules which are scattering the light, of which are scattering the sunlight, are is much less than lambda. So in that limit, you can actually treat these dust particles as independent oscillating dipoles. Okay, and this is the well-known Rayleigh limit. And in that case, absorption uh, coefficient, the absorption cross section is just given by this 4 pi omega by c, imaginary part of this alpha. Alpha is this electric polarizability. So they are all related. This alpha, epsilon, m, they're all related. They're all related to the material response, right? So alpha is electric polarizability of dust grain, and it is like it goes like the volume of the dust grain, a cube, right? So uh, you can imagine a dust grain, and you have like electric field applied in the electrostatic limit. Uh, Polarization P is like the density, the dense induced dipoles because of this because of being exposed to the external electric field. So this P is proportional to a cube. The larger the grain, the larger the induced dipole would be. The more the number of dipoles will be. It's sort of proportional to volume. So yes, polarizability can be complex. Like for metals, polarizability is complex. You can have imaginary part. It's just like for metals, right? Yeah, if you don't have a complex polarizability, you don't have any absorption. So this is absorption cross section. So absorption happens because of, I mean, you can think of it as a damped oscillator. The standard model for Rayleigh scattering is to do the damped oscillator and look at omega. So it's large lambda. So omega much less than omega naught limit. If you do the damped oscillator, right, there's resonance and all that. If you do omega less than omega naught, you'll get that response. And that is sort of what you can actually base all this on as well. Uh, so, so in that gamma, in that damped oscillator, this gamma is like an alpha. It's sort of linear, dissipative linear response. The scattering cross section, on the other hand, goes like this. here is that famous 1 by lambda to the 4, right? Omega by c to the 4. This can also be derived from dipole, dipole radiation formula also goes like this. So like a squared, right? If you look at the dipole, the power formula for radiation, it goes like acceleration squared. Acceleration goes like omega squared x. So this is omega to the 4. Okay, so these are, I mean, I'm just stating it. These are not derived in any way, but at least some of this we have come across that's in some form earlier. Now, now this goes like a cube or the volume v of the grains. So after solving this electrostatics problem, in fact, this problem for spheres can actually be solved exactly, and I'm pretty sure Jackson does it. So this is what you get. So the cross section for absorption goes like this. If you plug in alpha in terms of epsilons, this is what you get. It's proportional to the volume of the grain and 1 by lambda, and proportional to epsilon 2. Yeah, this is very clear, right? Absorption only happens if you have the imaginary part of epsilon. Otherwise, it's not does not happen. This is the scattered part. This does not require epsilon 2. So this is the general expression. Uh, Now you can actually see the dust grains can be made up of insulating material like silicates and so on. And it can also be made up of more conducting material. And so for the insulating materials, epsilon 1, the, the dissipative part of your dielectric function is a constant epsilon naught. Uh, sorry, not epsilon 1 is the real part. Epsilon 2 is the imaginary part. The epsilon 2 goes like a omega for insulators. And if you plug in that here, and for insulators, dissipation is small. It does not dissipate much, but the dissipation, so it's, if you plug that in, what you get is the absorption cross section and scattering cross section go like this. For conductors, you know, there is a different form for epsilon 2 because of this electrical conductivity. We are not going to go into the details. Let me just sort of show you the final expression. So the final expression has absorption cross section going like 1 over lambda squared. In both cases, actually, for insulators and for conductors. And the scattering cross section also going like 1 over lambda to the 4. This is in the Rayleigh limit when wavelength is bigger than the size of the dust grains. So this is good. So what it says is that for a range of minerals out of which these dust grains are formed, you expect scattering and absorption cross sections to go like 1 by lambda squared and 1 by lambda to the 4. And these are some solutions for spherical grains. As I said, this problem can actually be solved for spherical grains in the low, small grain size limit. So this is a very important parameter, a by lambda. When you're doing these scattering problems, the problems can be set up in a by lambda terms. So when lambda is much bigger than a, the Rayleigh scattering limit, which is on the left of these plots, you can see this is the absorption cross section, or absorption cross section divided by pi a naught squared. So it's normalized to the geometrical size. So as your a, as your, so left is the Rayleigh limit, and you can actually see this goes like lambda to the minus 2 because this is 1 by lambda on x-axis. So this has a slope 2. You can actually see that by eye as well. Okay, so this is the Rayleigh limit. This is absorption. For large a values, the other limit, when the lambda is small compared to the size of your absorber, you are in the geometric limit. It's like blocking the background light. So it approaches 1. Absorption approaches 1. And what are we showing here? Right. So this m is this refractive index. So this dot dash line has a real part of refractive index, which is 2, and the imaginary part of refractive index, which is 1. So this has a lot of absorption because the higher this imaginary part, larger is the dissipation or absorption. So this is 1, this is 0.1, these are all 0.01 and different values of the real part. So you can actually see, intuitively see that the smaller the value of imaginary part is, smaller the absorption. And all of them go like this power law at small a by lambda. This m was this refractive index value. And these are from numerical calculations. This regime is the Rayleigh regime on the left. The other regime on the right for large spherical particles is called the Mie scattering regime, when the particle size is comparable or bigger than lambda. So this is for absorption, this is for scattering. And this, again, this goes like lambda to the 4, or lambda to the minus 4. I mean, x to the 4 in this case, because x is 1 by lambda. And these are all different. So these are all the same. This is 2 plus I, this is 2 plus I. But scattering does not require dissipation to be there. So they're all very, very similar. Unlike these, the higher the imaginary part here is, the more the absorption coefficient. But here, there is no such trend. In fact, this with the highest dissipation is the lowest here. So here, you will actually see that as you are approaching the geometric limit on the right, there are these oscillations in some of these non-dissipative models. And that's because of these interference effects. So all these little induced dipoles, when their radiation is added, they can also sort of, they are added with the phase. So you can also have cancellations. So that's why you have these interference type patterns here. Okay. Similarly here too. Okay. This extinction is just the sum of these two. And if you look at extinction at small values of a by lambda, that is at large lambda, extinction is dominated by absorption, because absorption goes like lambda to the minus 2, whereas scattering goes like lambda to the minus 4. And this is basically the sum of these two. And what you'll see is this approaches 1, and the scattering also approaches 1 in the geometric limit. So the attenuation approaches 2. And this is sort of a puzzle, because if you have a big sphere blocking a light, you only expect the absorption, or you only expect to block pi a squared. Why is there a factor of 2? And apparently that's because of diffraction of light at these surfaces. So this is sort of called this is sort of a puzzle. Okay, but this asymptotes to 2, and scattering and absorption provide equal contribution in that limit. Okay. What about extinction as a function of wavelength for different grains? Okay. So here x-axis is lambda. It goes from almost X-rays to 100 micron far infrared. So what do we expect? So this is Q extinction. We expect a curve like this, right? This is Q extinction, total extinction cross section normalized to the geometrical area. So let's see. This is small lambda limit. Right? If A is fixed, if the size of the grains is fixed, on the right we are in the small lambda limit. So this is lambda. So this is the geometrical limit on the left. In this plot, geometrical limit is on the left. So if you look at a 10 micron micrometer grain, this is where you're this is 10 micron. This is where sort of approaching onto the left of this point, you are approaching the geometrical limit. Towards the right, you're going to the Rayleigh genes for that particular grain size. Okay, it sort of roughly looks like this. If you go to a 1 micron, of course, you expect this to just shift by a factor of 10 as you go smaller and smaller. Okay. The important thing that you'll start to notice here is that as you go to very small lambda, the grains start becoming transparent in X-rays. For small sized grains, they are transparent to X-rays. And you may also know that if you have looked at mirrors in X-ray telescopes like Chandra and XMM, if you take a normal mirror and shine X-ray on it, X-rays just leave. So it's only at very grazing incidence that X-rays are reflected. So it's sort of in X-rays, normal matter like these dielectric grains and so on behave in a very different way compared to say at larger lambda. This is one type of grains which are called astrosilicates. So you can see these X-ray absorption features, X-ray edges here. That's just because of the material out of which this grain is made. Um, in the infrared at A equals these, you see silicate. So these are those absorption features that we also see in our extinction curves at about the same wavelengths. Okay, so so this is what I was actually mentioning earlier, that some of the elements uh, in the interstellar medium condense out of the gas phase and populate the dust grain. So this is actually an observation of abundance relative to the solar abundance for a bunch of elements. Gas phase abundance is relative to solar in the diffuse cloud towards zeta of Fucus. This is a star. Uh, Plotted versus condensation temperature, T condensation. So condensation temperature is the temperature below which grains can exist in the solid form. If your temperature is above it, they are all evaporated, and again, their constituents become part of the gas phase. Uh, Solid symbols, major grain constituents. So these are the solid symbols. This, and this. These are some of the more abundant materials: calcium, magnesium, silicon, iron. The carbon abundance has been calculated assuming some oscillator strength for this particular transition. So the idea is the following. So look at this zeta of Fucus. Look at the absorption feature due to carbon 2, a singly ionized carbon at this wavelength. Uh, so model it. So you will know. So you know the distance to the star. You assume like it's sort of a homogeneous medium. Uh, you know the column of carbon 2. Uh, And so depending on this oscillator strength of this thing, so if the oscillator strength is large, then even a small amount of carbon will produce deeper absorption. If the oscillator strength is small, you'll get a smaller uh, absorption. So that's why the results depend on the oscillator strength. But oscillator strengths for most of these transitions are well known from lab data and from atomic calculations. So the apparent overabundance of sulfur here. So it looks like towards this sight line, sulfur in the gas phase is more than in the sun. The apparent overabundance of sulfur may be due to observational error, but may also arise because of S2 absorption in H2 region around gamma of you, around zeta of you. So, the real things are quite complicated. But you see, let's see. So this is krypton, oxygen, carbon, nitrogen. This one is where you expect if there was no condensation into dust grains. You see, look at this calcium. Almost all of the calcium is not in the gas phase. But we don't really talk so much about calcium because it's not one of the most abundant elements. So even if all of it is in the dust phase, it cannot be the major dust uh, contributor because its abundance is small. It's only these guys, carbon, oxygen, silicon, magnesium, and even iron, that we care about because their abundances are higher. And we know from this per cell limit that you have to have about more than 0.008 the mass of hydrogen in the ISM in dust form. Uh, so iron is also, a lot of iron is also depleted in dust. Similarly, uh, silicon, magnesium, and all these elements. So here is a table actually corresponding to the same observations. X is the element, NX by NH solar. So what is the abundance parts per million in the sun from modeling the solar spectrum? So number of carbon divided by number of hydrogen atoms in the sun. So the hydrogen atoms, this times 10 to the minus 6. That's the number abundance. So 300 times 10 to the minus 6 is the number abundance of carbon relative to hydrogen in the sun, and so on. You can see oxygen is the most abundant after that in terms of numbers. After that, it's carbon, magnesium, silicon, and iron in the sun. B is, this is the measurement in the gas phase. Okay, so from measurements like this, which model the absorption lines, you get about 135 as your abundance for carbon. So the rest of it is in the dust. And these two different answers come if you assume a different value of FC2, since for some of these oscillator strengths are not very well known. Uh, so you see here, majority of carbon is actually in dust. So about 135 in gas and 160 in dust, if you assume a certain value of F. Uh, this is the mass ratio of dust to in mass in dust to mass in hydrogen. This is about 2. So in the ISM, about a factor of 2 more mass resides in the grains. Mass of carbon resides in the grains than in gas phase. Like CO and all these emitting molecules have less carbon than dust. Some of these are forbidden lines. It requires extremely low densities to be able to do these. For example, you cannot do a 21 centimeter, you cannot produce a 21 centimeter line in the lab because even the lowest densities that you can create in the lab are much higher than, so the collisional de-excitation is faster than radiative de-excitation for these forbidden lines. For allowed lines, you can do all this in lab. So it is through atomic calculations. Good question. So this is nitrogen. So nitrogen is not that much depleted. Uh, so like there's a negative value for nitrogen and sulfur. For oxygen, about equal amount. Uh, Aluminum, almost all of aluminum is in dust. Uh, Similarly, silicon, uh, calcium, you see 0.0004, this is 2.2. Iron also is mostly in dust grains. Oh, I mean, so the error bar is bigger than the value, no? For those cases, you will see that. So the value came out to be that, but the error associated with it is very big. So it's consistent with 0. Um, right. So this is 10 to the 3 m dust by mh. This should be about, if you add all these up, this should be about 10, right? Because I said 0.01 of the mass of ISM is in dust. So if you add all these up, you should get about 10, which you do. So 2 plus 2, where you exceed 10 a little bit. And most of the mass is actually looks like from oxygen. Even though majority of oxygen is in the gas phase, most of the mass in the dust is contributed by oxygen because it's more abundant. And then after that, we have this one, carbon, and so on. So if you have oxygen, carbon, silicon, aluminum, so look at the minerals on the earth, silicates, uh, minerals with aluminum are very common even on earth. So a lot of these dust models are actually based on known substances, known minerals. So elements must condense into dust. And inert, so neon has a high abundance, but it's an inert gas. It does not react. It cannot form complex molecules and eventually these grains. So you cannot put inert particles into dust because they don't react. So in order to make a complicated things have to be reactive. Okay. What are the possible constituents of dust? So we have identified the elements, right? That there should be a lot of oxygen, carbon, aluminum, iron. But in what form, what compound should they form? Uh, so people consider silicates. So these are minerals, pyroxenes, which have composition like this. If you do courses in earth sciences, you'll encounter this all the time. So these magnesium, iron silicates, or olivines, which are somewhat different but very similar to these. Uh, then silicate, silicon dioxide, in fact, the terrestrial dust, uh, magnesium oxide, iron oxide. So you can have oxide, silicates, carbon solids like graphite, amorphous carbon, diamond. You can have these. Diamond requires a large pressure to form. So these have to be cooked in inside stars and this spread out. Uh, you can have hydrocarbons, polycyclic aromatic hydrocarbons, or PAHs. PAHs. So these are some uh, organic molecules, uh, which people think about when they talk about polycyclic aromatic hydrocarbons. You can actually see these rings, benzene-like rings. Uh, in fact, people have actually seen the spectral signatures of fullerene, this C60 ball, buckyballs. They have seen uh, signatures of that in spectra in the ISM. So you can have these balls, 3D structural, which look like a football. These kind of molecules existing in the interstellar medium. Carbides like silicon carbide or metallic iron. So these, given the elemental constituents, what you think about is what are the stable grain-like molecules that they can form, and these are kind of the possibilities. What about the size distribution? Like, grains have a range of sizes. If it had just one size, your attenuation and so on would look very different. So grains are about micron size, but that's just a typical size. There's a distribution in sizes of grains, which is roughly sort of indicated here. So let's see. What is plotted here is this quantity, 4 pi a to the 4 by 3 dn by dA. 4 pi by 3 a cube is the volume. So this is volume times a dn dA. Volume of the grain times a dn dA. So dn dA times dA is the number of dust particles with size a to a plus dA. So this is just the volume contained by dust grains in the range a log a ln a to d ln a plus d ln. So basically, if you choose a logarithmic scale in the size of the dust particles, and if this is flat, then you have about equal volume in equal logarithmic bands. So if you had a flat line like this, you had equal mass or volume across grain sizes. But here you see that it sort of increases. What it means is that most of the volume or most of the mass is in large dust grains, about a 0.1 micron. But most of the area is covered by, or most of the absorption is due to small dust grains. These are some of the well-known models of the dust models, right? So WD01, so D is Drain, whose book we are looking at, and he's like world's authority on grains, the interstellar medium grains. So this is some other model and so on. These are silicate grains. These are carbonaceous grains. Yeah. So I think we are actually done. So this was just the only part that I could actually do for dust in one class. But you get the idea, right? That they play a very important. Dust plays a very important role. What we have actually not covered is this part. How does dust catalyze the formation of H2? Chemistry mediated by dust. This is what we have not covered. How does dust affect thermodynamics of the ISM? So the photoelectrons produced by it. We have not covered this part, but that's fine. We have actually covered more or less the most important aspects of dust. Okay, so with that, we'll end the class.